Welcome to another session of Prof. Scangrella. And now we're looking at series circuits. So we will consider batteries in series, resistors in series, and also discuss parallel as well. So series circuits. Where does series circuits come? If I ask you to connect two components in series, I told you that we had two resistors right here, two components. I'm not just going to draw a block to represent them, and you were to connect them in series, right? Connecting them in series means that there's going to be one path for current to flow, right? It means that you're going to connect this guy to this guy. This is how you connect in series. And now you have this portion and this portion that you can connect to a particular load or whatever, right? So it means that you'll have one path for current to flow through the components. It could be like 10 components, whatever. Once you connect it in series, there's only one path for current to flow. If you were to connect these two in parallel, if I give you two other components, and I said connect these two in parallel. Connecting something in parallel means that there will be two paths or multiple paths for current to flow, right? Each item will have its own path for current to flow. And now you can connect this to a source or a load or whatever, right? So this would be parallel, P here. This would be series, right? Now, we are all familiar with batteries. We use batteries in our Game Boys or whatnot. And of course, each battery, the voltage across each battery chemistry is like 1.5 volts. And so most times we use multiple batteries in a device, and these batteries are connected in series so that the voltage is going to add up. Of course, we know that for this symbol, this is the positive side, this is the negative side. And we know that we need to connect positive to negative for the voltages to add up. Of course, if we connect negative to negative, it's not going to be adding up. It may be being subtracted, right? So the total voltage from these three batteries, if we were measuring here, we would get 4.5 volts, right? When we connect batteries in series, the other thing to note is that we only have one path for current to flow, and the maximum current we're going to get is the current output of the battery. So if the maximum current output was 1 ampere for each battery, the current flowing in the circuit would be 1 ampere, whilst the voltage would be the sum of the voltages. Now, if we connect batteries in parallel, what happens? Right, the battery voltage stays the same, right? So the voltage is still 1.5 volts for the battery, but the current is going to be increased. So the 1.5 amps from each battery will add up. So this will add up, and so the total current we have available is going to be equal to 3 amps. So whilst the voltage is still 1.5 volts, the current that is available is going to be 3 amperes because we have the current from each source. Whereas in the parallel circuit, it's not so. Sorry, in the series circuit, the current is still going to be 1 ampere, right? So again, we have all used batteries. We connect them in series so the voltages can add up. This same concept of adding positive to negative will be used for our series circuit as well. And as we continue in our course. So let's consider resistors in series now. So of course, we have been looking at our circuits with one load, right? One resistor. And so we're saying that we said that if our voltage source is 10 volts here, and you take your meter and you measure across this resistor, you will get 10 volts, right? So in other words, all of your voltage is dropped across your load, right? That is also a law of conservation of energy, right? We have a law called KVL, or Kirchhoff's voltage law. It says that the voltage drop here, which is 10 volts, is going to be equal to the voltage source. So you can say that Vs is equal to VR1. So VR1 stands for the voltage drop across R1. When we have resistors in series, what is happening? And we're going to use the same, we will use the same source of 10 volts. And this time, instead of having 10 ohms here, we're going to put 5 ohms here on this one. And we have another resistor with 5 ohms. 5 ohms. Well, in series, since we have only one path for current to flow, we are saying that the current will see all of this load, right? So it's going to see 5 ohms here and 5 ohms here. So the total resistance that the current will see, or the battery will see, is going to be the sum of the resistances. So this is the first principle when we deal with resistors in series, that the total resistance of the circuit is equal to the sum of the resistances, R1 plus R2, right? So in our case here, we can say that our total resistance is equal to 5 plus 5, which is equal to 10 ohms, right? So the current will see all of the resistors. It doesn't matter if we have 15, it will see all of them. And so the total, the current is going to be based on the total resistance, right? So now we can find the current. Again, we use Ohm's law to find the current. It's going to be the voltage source over the total resistance, right? And this gives us 10 volts over 10 ohms, which is 1 ampere. Right, so our current is 1 ampere. Notice over here, our current was equal to V over R, which was 10 volts over 10 ohms, which gives us 1 ampere as well. So even though, so again, you can see that the series circuit is just, we have the resistor, the same resistance broken up into smaller pieces, right? So you can see here we have 5 ohms that add up to 10 ohms. So we have the same current in the circuit because the resistance is the same. So far we have seen that in series circuits, the resistance is going to be equal to the sum of the resistances. Then we also saw that the current, we can find the current using Ohm's law, right? The second thing we need to consider in series circuit is the voltage drops, right? So again, we come back to this Kirchhoff voltage law that says that the voltage source must be equal to the voltage drops. Now in this case here, we have 2 voltage drops, right? We have Vs is going to be equal to VR1 plus VR2, right? So in other words, the total voltage drops here is going to be equal to Vs. So again, so like here, we have 10 volts right here, and after the load, we have 0 volts, right? The same thing will happen here, but instead of going to 0, we're going to have whatever voltage is across 5 volts. So we're going to have a voltage drop across 5. So we start with 10 and we drop some across this first resistor, and then we're going to drop the rest across the second resistor. Now the fact that they have the same resistance, we will see how this affects the voltage drop. So there are 2 ways we can find VR, right? How can we find VR? There are 2 ways. The first way is to use Ohm's law. And the second way to find the voltage drop is to use the voltage divider equation. All right, so let's find VR1 using Ohm's law. So VR1 is equal to what? Again, we said Ohm's law can be applied to the battery, right? Knowing the voltage drop across the battery, knowing the battery voltage and the current that the battery is supplying, we can find the load, right? We can also apply Ohm's law across a resistor. If we know the current flowing through the resistor, which is the same as our current we just found, and if we know the resistance of the resistor, we can find the voltage drop because we know that V is going to be equal to I times R, okay? I times R1, and so that gives us 1 ampere times 5 ohms, which will give us 5 volts, right? So this is the first way we can find voltage drops, by applying Ohm's law to the resistor. The second way we can find Ohm's law is by using the voltage divider equation. And again, this equation is based on the fact that the amount of voltage drop across a resistor is based on the resistance. And so the larger the resistor, the larger the voltage drop. In this case here, we have the same resistance, so we're going to have the same voltage drop. So again, you see here, it's going to be VR2. Let's find VR2 using the voltage divider equation. We're going to have R2 over the total resistance, RT. So we are taking the fraction of R2 over RT, and we are multiplying that fraction by our source voltage. And that is correct because we know that our source voltage is going to equal to the sum of the voltage drops. So this is a fraction of Vs. This one is also a fraction of Vs. And so here we get 5 over 10, which is a half, times 10. And that gives us 5 volts as well. All right, so this is again, we found the voltage drop using Ohm's law and using the voltage divider equation. What about power? If you wanted to find power in a series circuit, how can we do it? Well, of course, the power is, you can find the power based on the power supply. And if you wanted the power for each load, we could find that as well. So in this case here, if you wanted to find the power across resistor 1, we can say power is going to be VR1 times I. We can easily do that. Or we could use V squared, VR1 squared over R, so that we can use the equations and find power. So this way we have 5 volts times 1 ampere, which gives us 5 watts. So if this resistor is 5 watts, this one also is 5 watts. And so the total power dissipation of the circuit that the circuit converts is going to be equal to 10 watts. So we can say that P2 is equal to 5 watts and the total power PT is going to be equal to 10 watts. All right, so again, just to reiterate, in a series circuit, the total resistance is the sum of the resistors. The current is going to be voltage over resistance. The voltage drops we can find independently using Ohm's law or using the voltage divider equation. And power is going to be independent for each resistor, and the total power converted by the resistors is the total power converted by the circuit. Okay, I have an example here so I went to the simulation tool online on Multisim Live. This is what I use for this. I'll just write it down in case you don't know. Multisim Live. So you can create a free account and you can simulate your circuit. You can create the circuit and measure the voltage at different points. So again, here we have 3 resistors. Our total voltage source is 24 volts. And of course, we have a voltage drop going down here. So here I decided, so the first resistance is 1.5K. The second one is 220 ohms. And the third one is 680. Now, based on what we just said with the voltage divider equation, we said the larger the resistance, the larger the voltage drop. So we expect the most voltage drop to be across here, the 1.5, and we expect the smallest voltage drop to be across here. Okay, so the current, right? The current was measured to be 10 milliamps. Okay, now in this simulation environment, we cannot actually measure the voltage drop, but we can measure the voltage at different points. So for example, at this point here, the voltage is 24 volts. When we come here, the voltage is still 24 volts here at this point right here. After the first resistor, guess what? We're going to have a voltage drop, right? So the way we can see the voltage drop, we need to subtract 9 from 24 to know what the voltage drop was here. So let's do that. So we can say that VR1 is going to be equal to 24 minus 9, which gives us what? I think it's that. Okay, let me calculate that. All right, so this is 15 volts present here. So the voltage drop across R1 was 15. Now we add 9 volts here, and after the second resistor, so we have a drop across the second resistor, our voltage went down to 6.8. So to find VR2, we need to say 9 minus 6.8. And that gives us 2.2 volts. So this is the voltage drop so far. Now, of course, when we come to the last resistor, the voltage measurement that we see here is actually the voltage drop. So VR3 is actually 6.8 volts, right? So again, all of this we can get from the simulation, right? Now, we did not measure the total resistance, but we can go ahead and calculate it. Based on what we said that RT is going to be equal to the sum of the resistances, right? R1 plus R2 plus R3. So of course here, to substitute here, we have 1.5. This is the same, 1.5K is the same as 1500. So I'll just write 1500 here, plus 220, plus 680. All right, and that gives us 2400, which is the same as 2.4K. All right, so now having the resistance, we can find the current, right? The current is going to be equal to, according to Ohm's law, Vs over RT, and that gives us 24 volts over 2.4K, 2400, which will give us 10 milliamps, or 0.01 ampere, which is the same as 10 milliamps. All right, so again, so we can see that our current is correct. Now let's go ahead and calculate the voltage drops for this circuit using the two methods that we discussed, which is the Ohm's law and also the Kirchhoff voltage law. All right, and we will verify if the simulation is correct. Okay, so let's start with VR1. VR1 is equal to, let's use Ohm's law for VR1. VR1 is going to be equal to I times R1, which is equal to 0.01 ampere times 1500 ohms. And that gives us 15 volts. All right. Let's calculate VR2 using the voltage divider equation. So V2, let's say, is going to be equal to R2 over RT times Vs, which is equal to 220 over 2400 times 24. And that gives us 2.2 volts. All right. So, and again, most times if you are told to find VR3, since we know Kirchhoff's voltage law that VR1 plus VR2 plus VR3 must equal to Vs. We talked about KVL. KVL says that Vs is equal to VR1 plus VR2 plus VR3. We can simply subtract and we can find our, okay, hold on. We can simply subtract and find our VR3. So we can say that VR3 is going to equal to 24 minus 15 minus 2.2. And that gives us 6.8 volts. All right, so again, just to recap, with our circuit, this is the same voltage drops that we calculated earlier from our simulation. All right, again, just to recap, for the series circuit, we are saying that first we need to understand finding the resistance. Secondly, we need to find the current, right, using Ohm's law. And thirdly, we can apply Ohm's law to the resistors to find the voltage drops, right? And again, we also stress on Kirchhoff's voltage law that says that the sum of the voltage drops should equal to the sum of the supply, right? This is it for our series circuits. And again, like I said, we can connect other components in series as well. We just calculated the for circuits with resistors. But if you were given some capacitors and you were told to connect them in series, of course, this would be how you would connect capacitors in series. Anything with two legs or two leads. If we had inductors and we're told to connect them in series, we'd connect them this way. Again, this way would be parallel. If we did this would be parallel. And this is what we're going to consider in our next lesson. How do we analyze resistors in parallel? Okay. Again, this is Prof. Scangrella. Catch you on the next one.